When you use hydrological models, routing isn't an optional step. It's built into every simulation. These tools automatically transform the inflow hydrograph as water moves through channels, reservoirs, and other drainage assets. But here is the catch. Each model does routing differently. This is a crucial step in hydrological modeling, as selecting the wrong routing setup can lead to underestimated floods, unreliable designs, and costly decisions. In this series, we reveal exactly how routing is implemented in the most widely used hydrological models, discussing the methods, assumptions, and parameters that can make or break your results. Today, we start with HEC-HMS, choosing the right routing method and parameters for your catchment. Let's get started. HEC-HMS is a widely used hydrological simulation software developed by the U.S. Army Corps of Engineers to model precipitation runoff process in dendritic watershed systems. It operates primarily as a semi-distributed, lumped parameter model with some spatially distributed capabilities designed to simulate both short-term flood events and continuous long-term hydrology. For channel routing, HEC-HMS offers at least 8 different methods, including lag method, Muskingum-Cunge, and Kinematic Wave. The user must select the method that is most appropriate for the study's purpose, the watershed physical characteristics, and the available data. Here we only cover the 4 most widely used. Let's start with the lag method. This simplistic method only shifts or translates the inflow to outflow without any attenuation. The only required parameter is the time lag. This is best for short reaches with predictable travel time or preliminary screening of non-critical reaches. The next one is Muskingum method. This method can capture both translation and attenuation well after calibration. The key parameters in this method are K, the Muskingum travel time in hours, X, the dimensionless weighting factor, and N, the number of subreaches, an integer used to improve numerical accuracy. We generally find appropriate K and X through a calibration process. Alternatively, we can also estimate them. For more details on this, please watch our video on Muskingum method. Now let's get back to N, the number of subreaches. If a reach is very long, means large K, a single calculation step can introduce excessive numerical diffusion, which is non-physical attenuation that results from the calculation method itself. HEC-HMS allows the user to divide the long reach into n smaller subreaches and significantly improves the physical accuracy of the results. It can be estimated by n equal to total length divided by celerity times delta t. Muskingum method is best for catchments with gauge reaches where you have historical inflow and outflow records to find K and X through calibration. The next method is Muskingum-Cunge, an enhanced form of the original Muskingum method developed by Cunge in 1969. Instead of entering calibrated K and X values, this approach uses the channel's physical characteristics to automatically compute K and X. This is one of the most widely used routing options in HEC-HMS and can capture both translation and attenuation. The required parameters are reach length, channel slope, Manning's roughness coefficient N, and reach cross-section shape. This method is best for on-gauge catchments, general stream modeling, and reaches with no significant backwater effect. The last one is Kinematic Wave. This method effectively translates the hydrograph without attenuating the peak unless numerical diffusion occurs. This is a simplified hydraulic routing method and needs the following physical parameters to work: reach length, slope, Manning's roughness N, and the reach cross-section shape, similar to Muskingum-Cunge method. As this method ignores the inertial and pressure terms in the momentum equation, it is best suited to steep, fast-flowing catchments such as urban ones with several concrete-lined channels. By ignoring wedge storage and diffusion, it may overestimate peak flows in natural mild slope rivers where attenuation is important. Now let's talk about reservoir routing. For routing in reservoirs and detention ponds, HEC-HMS has the direct implementation of level pool routing or modified pulse method. The user provides the physical data required to build the storage indication curve. The required data is a storage-discharge relationship, which comes as a table relating storage volume directly to outflow discharge. Or alternatively, the elevation-storage-discharge relationship, where the user can provide an elevation storage curve and an elevation discharge curve, which the model combines. HEC-HMS then takes these user-supplied data, combines it with the simulation time step, and internally computes the lookup table or fitted formula for 2s over delta t plus q versus q. It then executes the exact iterative routing calculation, which is common in the level pool routing process. If you are interested in knowing more about the details of this method, please watch our tutorial video on level pool routing. Today we learned how HEC-HMS handles flow routing, from simple routing options like lag method to more advanced one like Muskingum-Cunge. Each option comes with its own assumptions, parameters, and limitations, and choosing the right one can make all the difference in your flood modeling results. In the next episode, we are shifting to RORP to explore how routing is implemented there and how its approach compares to what we have seen today. If you want to continue building confidence in your hydrological modeling, please make sure you don't miss it. Thank you for watching. See you in the next one.